It's so wonderful to see everybody's faces. I'm so glad you were all able to join us today for this really incredible talk. I first want to thank Rachel, Hallie, and the entire Bulletin team for making this possible today. And it's such a pleasure to introduce our esteemed speakers, Vicky Kalogera and Daniel Holz. Vicky is the co-founder and current director of the Center for Interdisciplinary Exploration and Research in Astrophysics, and the Daniel I. Linzer Distinguished University Professor in the Department of Physics and Astronomy in the Weinberg College of Arts and Sciences at Northwestern. She's a leading astrophysicist in the LIGO scientific collaboration, where she has been a member for more than 15 years. She was elected a member of the U.S. National Academy of Sciences in 2018 and was recently awarded the Heinemann Prize for Astrophysics by the American Institute for Physics and the American Astronomical Society. I have to add, I did edit down both her and Daniel's bios because they're so unbelievably impressive. Daniel is a professor at the University of Chicago in the Department of Physics, Astronomy, and Astrophysics, the Enrico Fermi Institute, and the Kavli Institute for Cosmological Physics. He is also a member of the LIGO scientific collaboration and was part of the team that announced the first detection of gravitational waves in early 2016 and the first multi-messenger detection of a binary neutron star in 2017. He received a 2012 National Science Foundation Career Award, the 2015 Quantrell Award for Excellence in Undergraduate Teaching, and the Breakthrough Prize in Fundamental Physics in 2016. Holz was selected as a Kavli Fellow of the National Academy of Sciences and is a Fellow of the American Physical Society. Daniel also sits on the Bulletin Science and Security Board. Welcome, Daniel and Vicky. We are so excited to talk to you today. So if Daniel and Vicky will both unmute themselves, we will get going on this. So Vicky, our first question today is for you. Can you explain what gravitational waves are and how the discovery of gravitational waves in 2016 truly changed the way we understand the universe?
Oh, how much time do we have?
We're going to get all these questions in 5 minutes or less, Vicky. Just the nature of the universe in a couple minutes.
So first of all, thank you for the invitation. It's a pleasure to be here with you, Cyndi and Daniel. And it's really the first time I do an event like this where everybody's face is on the screen. And finally, it's a very different feeling to not be talking into the vacuum. Okay, so back to your question. What are gravitational waves? So let me start from the basics. It's basically, it's a wave. It's a wave that exists in nature. And as every wave, it's an oscillation of something. So most everybody is familiar with electromagnetic waves. And this is how we have studied the universe for centuries. Electromagnetic waves are oscillations of electric and magnetic fields. And they have a wide spectrum, many different frequencies or wavelengths, the length of one oscillation that covers many orders of magnitude of length scales. So for astronomy, we have used the full electromagnetic spectrum from radio waves that are quite long to the shortest wavelengths we have mastered to use as tools to study the universe, which is the gamma rays. Gravitational waves is another type of wave, another type of oscillation. And the thing that oscillates is actually the curvature, or if you want to think about it more simply, the shape of space-time. And for our discussion today is actually perfectly fine to just think of just space. So if we think of the space around us, the three-dimensional space, it turns out that space around us is not static, but it can be curved. It can be, the shape of space around us can be changed because of the presence of mass. And if that mass is moving and especially accelerating, then the curvature, the shape of space, can be changed as a function of time. And depending on the motion of the mass and the acceleration of the mass, that motion can be oscillatory. So masses that get accelerated in a particular way, in a way where the motion of the mass is such that the silhouette of that motion with respect to our line of sight is actually changing, then that kind of mass motion can make the shape of space, the curvature of space, oscillate with particular frequencies, just like electromagnetic waves can oscillate with particular frequencies. And those waves propagate throughout the universe.
And so what is it about what we've been seeing as of late that is so transformational about what we're learning? And Daniel, I'm going to kick this over to you now. I know there have been a lot of different discoveries over the past few years that have led to what we've just found in June. Can you give us a little bit of a background about what we've learned over the past few years and why it matters, and why, especially people, those of us who are not scientists on this talk, what does this mean for the layperson? What is it we're learning about our world, about ourselves, and about our universe?
Yeah, okay. Well, first, thanks for having me, and it's really great to be here and see so many people interested in black holes and gravitational waves. And yeah, it's been a pretty exciting few years. As Vicky described, gravitational waves were this prediction of Einstein's theory of general relativity. He predicted them over a century ago, and really at the time thought we probably would never detect them. And for decades, people have been working and building a detector and trying to find ways to detect these incredibly tiny vibrations in space-time. And what the big news, the reason we're all here today, is that about 5 years ago, in 2015, we turned on this LIGO detector, and it was at a sensitivity such that we finally thought we were likely to detect something. And 2 days after turning on, we did in fact detect something. We detected what we affectionately call GW 150914, which means it occurred in 2015 on September 14th. We really need to work on our naming scheme. That's one of the things that we actually have a committee to work on our naming scheme. But that discovery was, we detected ripples in space-time in our two detectors, one in Hanford, Washington, one in Livingston, Louisiana. At the same time, there were these ripples. We could hear them. And by measuring those, we inferred that that was two black holes colliding, two fairly big black holes, each of them about 30 times the mass of the sun colliding. And so just detecting gravitational waves and then detecting gravitational waves from black holes, where we could analyze the details and say, well, those were two black holes. Yeah, that was quite transformational. I mean, those were two big firsts. And so that was extremely exciting, and both Vicky and I were involved in that. And, at the time, I certainly thought that was, the peak of my career. It was never going to get any better. This was a major discovery. We all wrote this paper. We knew this was going to be, one of those papers everyone talks about for, decades or centuries, maybe. It was fantastic. The Nobel Prize was awarded for the discovery in very short order. That was really thrilling. But that was just the first. And what's been most exciting, and I think Vicky really was one of the very first people in the entire community to realize this, the point here wasn't that we would get that first discovery, it's that we would be able to do astronomy, that we would keep on listening to the universe and hearing more black holes and other things colliding. And that's exactly what's happened. In 2017, we heard two neutron stars colliding. And that was another truly transformational, I would argue even more exciting discovery, because in that case, not only did we hear the objects in gravitational waves, but they collided and they created this giant explosion, and we saw that explosion in light with our normal telescopes. We saw it in gamma rays, we saw it in optical, we saw it in radio, in radio frequency light. So across the full electromagnetic spectrum. And that was phenomenal and taught us a lot about the universe. But that's just, again, just one more. We've continued to observe, to listen to the universe. And at this point, we have something like 50 different sources that we've heard, collisions that we've heard with our detectors. About a month ago, I guess in late June, we announced the discovery of what we call 1908-14, which was a bigger black hole with a small object which is either the smallest black hole ever or the largest neutron star ever. And that's something, Vicky can talk about. That was extremely unsettling and exciting, and we're not sure what it was. And then we just announced a few weeks ago in early September, the discovery of two black holes that are just too big, if you like. They're in this region where the theory says they shouldn't exist, the universe should not be able to make black holes of this size, and we detected two of them colliding into each other. And that's the latest mystery, and that's gotten us very excited as well. So it's been this whole series of discoveries. It's really been remarkable.
So Vicky, I would love to have you tell us a little bit more about the most recent discovery, what it means for us. But what we talked about is one of the most incredible things that blows my mind is that what we're doing is listening to sort of the ancient universe in real time. And you actually can tell size of black holes and what's happening through these sounds. And so Daniel, if you don't mind screen sharing so that everybody can hear these sounds that you all heard. And Vicky, maybe after we listen to the sounds, you can tell us a little more about what they mean and what you amazing scientists have been able to figure out as a result of hearing these very abstract, amazing sounds.
So let's listen to the sounds first, then I'll talk.
Perfect.
Okay, so this is the sound. So I'm going to play first the sound of the two black holes, the very first discovery. And, there are some pictures, there'll be some video here. And what I'm plotting, just for those that, kind of have a more scientific background, is the frequency, so the pitch, as a function of time. And how bright something is tells you how much there is at that pitch. So this is kind of a visual way to listen, if you like. And as you move up on these plots, that means you're moving to high frequency. And so I'm just going to plot. This is what we heard. The top one is we have two detectors. The top one is in the Hanford detector. The bottom one is Livingston. And here's what we heard. I'm going to play it, then I'll repeat it. And then I'm going to play it at higher frequency, just shifting it a little bit just to make it easier for you to hear it. And so it'll keep repeating. Here we go. So just to go back to that. So what you hear is a little thump. So that's what we actually heard in our detector. That's incredibly loud for us, ridiculously loud. And then you can hear the very distinct chirp. It's much easier to hear at the higher frequency. I mean, that is the chirp. That's what Einstein predicted we should hear. And then that's what we got. So that's the sound. I mean, we're taking the gravitational waves and turning it into sound. Just to be clear, it's not actually sound. It's vibrations in space-time, as Vicky described, but those vibrations happen to be in the audible band, and there are various other aspects of it that make it more like listening than seeing. We can talk about that if there's interest at the end. And so we just turn it into sound, make it much, much louder, and then we put it into the speakers, and that's what you're hearing. So I'll play these again, and then I'll play the other event. Okay, so those were the two black holes. Now I'm going to play the same thing, but so same idea, but this is going to be for this other event that we heard in 2017, a couple of years later. And this is two neutron stars. And it's now, I'm not shifting the frequency because the neutron stars are smaller, less massive, they're at higher pitch. And you'll just be able to hear this. I'm not messing with it at all. And you'll hear it. Then there'll also be a ding, and that ding I'll talk about right after. But first, here's the gravitational wave. Okay, so that sound, that chirp, is precisely what was predicted. It was incredibly loud for us by our measures, and it was just crystal clear. It was this beautiful chirp, and so we detected that, and that's this one where we were also able to point our telescopes. What happened is 2 seconds after, and this is sort of real time if you like, you hear the gravitational waves, 2 seconds after there's that ding. That ding is a burst of gamma rays hitting some of our gamma ray satellites. And that combination had never happened before, where we're listening to the universe and seeing the universe at the same time. And so I'll play this once more and then we can go to Vicky.
That's fantastic. So Vicky, hearing these sounds from a layperson, I would never know what any of this is. And when we were talking about what these discoveries mean,
yes,
you gave the most beautiful metaphor when we were talking about this before, about the silent film. So I was thinking maybe you could talk a little bit about that for context, and just remembering that we're all not scientists in this group. And so how does that translate to meaning? And then talk a little bit about what we've learned and what this latest discovery has changed about the way that we think about how black holes are formed.
Yes. So let me cover a couple of different things. So I'm gonna take a step back first and make sure that we don't have a misunderstanding here. So we started telling you about electromagnetic waves and oscillations of electric and magnetic fields. Then we told you about oscillations of space and shapes of space. And then we jumped into sounds, okay? And as Daniel said, it's important that our audience doesn't get the idea that gravitational waves are sounds, because they're not, okay? So the sound analogy is a good analogy that we use for gravitational waves for two reasons. One is completely accidental, and the other actually has more meaning. The sound analogy and the way we transform our actual gravitational wave signals, which we have now received, or we simulate in computers, into sound, we do it for two reasons. One is that the frequency of the waves we have received from nature so far, it's the range of frequencies that our detectors, the LIGO that were mentioned and the Virgo detectors, are actually sensitive to. So this is in a way, it's a selection effect. Just like in the beginning of astronomy, all we could see was optical waves, because our first telescope was our eye, and the first generation of telescopes for many years were optical telescopes. It was lenses that can only detect optical light. So now we have detectors of gravitational waves. They're very weird telescopes. They don't look like normal telescopes at all. They use lasers and they can detect gravitational waves in the regime of frequencies that go between, let's say, roughly 30 hertz to maybe 500 hertz. That regime is similar to the range of frequencies that our ear is sensitive to when it comes to sound waves, okay? So the A note is about 440 hertz, all right? So it is an easy translation from one wave to another, and we can take our gravitational wave signals, follow their frequency evolution as a gravitational wave, and just recode it into a sound wave so we can listen to it, because gravitational waves don't give us images. So we cannot give you a nice Hubble image of the gravitational wave universe, but we can give you a concert of gravitational wave signals. So that's the coincidental analogy with sound. There is a more meaningful analogy with sound, which is the following: the detectors themselves. In electromagnetic astronomy, especially optical astronomy, which more of us understand intuitively, the telescopes act, or also X-rays and a few other telescopes in astronomy, they act like our eye. So they have to point. just like our eye. We cannot see unless our head points in the right direction. But gravitational wave telescopes are not pointing systems. They can stay on the Earth and they can receive gravitational wave signals from all directions. And in that sense, gravitational wave detectors act like our ears. Our ears don't have to point in a certain direction to listen to a sound. We can hear sounds from all over. We can hear sounds from above, behind us, under us, etc. Yes, we hear better if we point our ears in a centered direction, but we hear sounds from all over the three-dimensional space. So in that sense, gravitational wave detectors are more like human ears, while most of electromagnetic telescopes are like human eyes. So that's the analogy. Now, in terms of what it did to our understanding of the universe, we call the gravitational waves a new messenger. It's a new way, a new window onto the universe. And we often think about it as a transformation for how we can study the universe. And I often liken it to the change in culture we had when in human culture we transformed, we made the transition because of technology between silent movies and movies with sound. So because of the transition in technology capability, we added in our movie culture a new capability, and think of what kind of transformation that was, not only in movies, but also in news and reporting and understanding the world. How adding sound onto video, onto silent video, has changed our perception of our human world. In the same way, gravitational waves are adding sound to our silent movies of our universe.
Vicky, that's such a wonderful way for all of us to understand how exciting and transformational these discoveries have been. Daniel, I have one more question for you before we turn it over to audience questions. In a lot of the interviews and in what we've talked about in the past, you describe some of these discoveries as both hugely frustrating or disappointing and exciting, because they're changing the assumptions that we make and the theories that we have about the way the universe operates and what is and is not possible. And these sort of mid-sized black holes shouldn't exist, and yet they do. So can you talk a little bit about what these discoveries mean in terms of the way we look at science, the assumptions we're making? You know, we've proven Einstein right. What's the next step, and sort of what's your sort of aspirational vision for what happens after, you know, this latest discovery?
Well, it is, I mean, it's been thrilling to be part of this. And, you know, this is the way science kind of, you know, when you're a kid, you have this vision of what science will be like. And it turns out this really is what science can be like and is like. And so in this case, this was something where there had been predictions. We turned on our detectors, and they worked. And the technology behind which, you know, Vicky alluded to, the technology behind these instruments is phenomenal. And there's quantum mechanics and lasers and all sorts of incredible things going on there. But the fact that all of that was able to happen and we could actually push the technology to the very limit and get them to work, okay, that's amazing. And then we turn it on and we hear these black holes, and what we hear agrees with Einstein's prediction. Okay, so all of that was phenomenal. It's exactly what you want. But what you also, I mean, it's pretty depressing at the end of the day if everything agrees perfectly. I mean, okay, that's fine, but then, you know, it's harder to get excited about. What has happened is the first couple of things agreed really well. That's, you know, terrific. But now we're starting to, as we get more, and this is the way science often works, as now we have what we call a population, this is becoming a more regular thing, we're starting to find things that don't fit, that are oddballs, and that, you know, aren't quite what we expected. Now, just to be clear, these all still agree with Einstein's theory of general relativity. It's not that they're changing fundamental physics. But what makes them odd is we just don't understand how the universe makes them. So, you know, Einstein says you can make a black hole of any size, but, you know, if you wanted to turn the Earth into a black hole, you have to squeeze it down to about this big. And the entire Earth has to be that big. And then you've made your black hole. And we don't know how to do that. I mean, we can't squeeze the Earth down. And we don't have any process in astronomy that we can think of. Well, I mean, there's some creative people that have come up with it, but it's very hard to come up with a way to make a black hole this big. We have lots of explanations for how to make black holes that are roughly the mass of the sun, or, you know, say 10 times the mass of the sun, or 20 times the mass of our sun. That we can do. But lately, we're starting to see things. For example, this latest discovery, there's a black hole that's 85 times the mass of the sun. That our theories say pretty robustly, if you want to take a star and collapse it and make a black hole that's 85 times the mass of the sun, that you almost certainly can't do. So that's where the theory was for a long time. For the last few years, we haven't seen any black holes that big. So, you know, I've written lots of papers saying that's what, you know, we expected. Everything fits perfectly. It's all great. And then we discovered 2 of these black holes right where they're not supposed to be. And so now something's up. And that part is, you know, it is annoying. And, you know, you have your nice theory, everything fits, and then the whole house of cards starts to crumble because you detect something that wasn't supposed to be there. But that's, you know, that's thrilling. We got to figure it out. We got to detect more. You want to be surprised. That go, Vicky.
Vicky, do you have any final comments about sort of the change in finding all these things and sort of the possibility of what we might find next?
Yeah. So this is the beginning of a whole astrophysics field, because imagine, you know, right now, Daniel Early, he said we have about 50 gravitational wave sources that we know. We haven't announced. In just a few weeks, we will announce the properties of all of them. And already with these 50, we have made measurements that were not possible before. We have discovered sources, the collisions of black holes that were always predicted, well, not always, but for many decades predicted and now confirmed. And we have already discovered things that are not meant to be. And we're trying to understand how nature makes it possible. But we're in the beginning. I mean, imagine where we were when we only knew 50 stars around us. Where were we in our understanding of the universe when we only knew 50 galaxies around us? There's an enormous amount of knowledge about the universe that came after that point. And we have that future in gravitational wave astronomy lies ahead of us. And we can upgrade, and we are upgrading the current detectors that have been built, and they can upgrade with a lot of effort, but not with building brand new detectors from scratch. And we have plans for actually building brand new detectors in the future, because eventually you do build new telescopes in every field. And there is plans and active building of space gravitational wave telescopes that will allow us to actually expand the spectrum. And imagine, and we are imagining, we're making predictions, but also imagine what surprises those observations are gonna bring. So the gravitational wave astronomy field is where regular astronomy was, you know, a few centuries ago. So that prospect is what makes us really have goosebumps when we actually sit down and think about it. Usually at events like this, we don't think about this every single day. Usually we have our heads down, sort of working on regular work. But this is what's coming for generations ahead of us.
Well, this is so inspiring. And I know that, you know, so many of us have been frustrated and the world seems so challenging right now. And so hearing about the magic of the universe has definitely been something that I have been loving learning about the past couple weeks, and I hope that our audience has been so inspired as well. I'm going to send it back to Hallie right now. She's going to talk about how we're going to do the Q&A for the next half hour, and then we'll get ready for everybody to get your questions ready.
Thanks, Cyndi. Hello again. As a reminder, my name is Hallie Posner, and I am the program coordinator here at the Bulletin. We do ask that you please keep yourself on mute throughout the program, unless you're called on for a question. But please keep your cameras on, as we are striving to build community, and each of you is our community. If you have a question for our speakers or moderator, please use the raise hand function. Our moderator will see that and call on you. You can find this by clicking on the participants button at the bottom of your screen. Please do not physically raise your hand. There are too many participants for us to recognize you in that way. Also, please note that we have many folks on the call, so we apologize in advance if we do not get to your question. If you've raised your hand, rest assured we see you, but we are unlikely to get to all questions. A recording of this program will be available on our website in the coming days. Back to you, Cyndi.
All right, so Brenda, you were the first one with a question. Go for it. Brenda, are you on mute?
Sorry. David. I'm using my partner's iPad. Just a quick question. So in relation to the source of the gravitational waves, would it be feasible to assume that because of the time-space curvature, that the wave that we are perceiving here would be of a different relative frequency to what the actual disturbance on the source was?
Yeah,
And
I can. Okay. Yeah. So that's a very interesting question. So the sources we're detecting are quite far away by cosmological standards, even. So there are lots of things that can affect what we detect. And of course, because they're far away, how loud they are, they get diminished in terms of how loud they are. But as you say, the sound can also be affected. One of the things about our universe that we know is that the universe is expanding. And because it's expanding, there's an effect which we call the redshift, which is like the Doppler shift. It's like when an ambulance goes by, as the ambulance is going away from you, the pitch of the siren goes down. And because the universe is expanding, when we see light or when we listen to gravitational waves, the pitch goes down. And that's something that we detect. And so what we actually detect in our detectors on Earth is different from what was emitted, and we can account for that, and that helps us understand what's going on. So that's an excellent point.
That's great. Thank you.
I would add very quickly to that even though, so they are affected because of the cosmological expansion, but unlike light, they actually have gravitational waves have very little interaction with regular matter. So in that sense, they're very useful because they can travel and they are transparent to regular matter. They don't get absorbed and hidden and blocked by regular matter. So we get information about the source directly. On the other hand, this is why it is very difficult to detect them. The signals are extremely weak, and this is why it took so long to detect them. And this is why Einstein thought it would be impossible to detect them, because the gravitational waves are interacting, have very weak interaction with matter. Therefore, they have very weak interaction with our detectors. So the technology for that took a long time to develop, and the idea for how to actually detect them.
So when I call on people, if you'll also introduce yourself so we know where you're from and who you are, that'd be great. So our next question is Andrea.
Yes, thank you very much. Andrea Bourgeois, I'm an engineering professor in France and board member of the Institute of Technology, government body. Just a question on perspective. If you can see or foresee a convergence, I would say maybe a singularity of your research field with other as yet undetectable phenomena or theoretical fields like black matter and energy, what would you think would be your next steps in research or collaboration?
So for now, we have a lot to explore still in connection to astrophysical black holes. And in terms of our detector development, we are not close to probing sources that are potentially connected to dark matter or primordial black holes from the very early universe or signals from the very, very early universe. However, we are already studying advanced next generation detectors that will have that capability. And we're always looking for signals in our data, our current data, that might not fit the expectations and might give signatures of, might be signatures of new fundamental physics that might have to do with maybe dark matter particles or phenomena that happened in the very early universe. But right now, we don't have an obvious path towards the expected detections that will make that connection with the detectors that are operating now.
Yeah, I might just add, I mean, so for example, and this is always true, so when we first detected the black holes, these 30 solar mass black holes, there was a lot of activity in the community because people thought maybe that is the dark matter. You know, so the universe, where our cosmological theories say the universe is filled with dark matter, maybe it's just black holes. It turns out when you're examining that closely, it doesn't really quite fit. So I think there's a consensus now that we're not detecting the dark matter. But that's a sort of thing where, because we have this new window on the universe, you know, we can make these radical new discoveries. I will mention we can use these gravitational wave sources as tools to learn about the universe. And one of the things we're doing is trying to have a better sense of dark energy and measure the expansion history of the universe and learn about dark energy and dark matter that way. So we're using them as observational tools, as probes, to learn more about the universe directly.
Fantastic. We have Gary Evans.
Hi, thank you all for doing this. This is fantastic, really fantastic. So I'm a dabbler in amateur radio astronomy, just that much. And I've got a couple of questions. One, what information might be encoded in gravitational waves, in addition to just the mass, I shouldn't say just the mass, but the masses of these colliding objects, spin and so forth? Is there any other information that might be modulated on the signal? And then another question is, how much actual energy, can you give us an idea of how much actual energy is embedded in these gravitational waves? Thank you.
So Daniel, I'm going to ask for help with refreshing some of my memory, but I'm going to start with the first part of your question, Gary. So what we receive is basically a time series of how space was disturbed in terms of a wave, and we study the frequency as a function of time. It was shown in the sound and visual that Daniel showed. So we have frequency as a function of time that allows us to extract the frequency derivative. And from the amplitude of the wave, we also, in contrast with electromagnetic waves, we measure directly the amplitude of the oscillation instead of the energy in the oscillation in the wave. So from these basic measurements, combined also with the fact that we have multiple detectors, and that's very important, we extract the masses, as we already mentioned. we can extract, we don't always extract, but we can in principle extract the spins of the black holes. It depends on the magnitude of the spins. It depends on the orientation of the spins with respect to us and in the orbit of the binary merging. And it depends on the location on the sky. We can extract information about where the source is on the sky and also how far away it is. We can measure these are connected to the polarization of the signal, and having more than one detector allows us to break and decompose the polarization of the signal in the two detectors. So I think that sort of gives the big picture. When two black holes collide, there is, of course, they don't collide in a direct collision. They're in spiral, like the waves behind Daniel's head. They're in spiral, and as they orbit one around the other, they're messing up space-time, and they generate waves. The waves carry energy and angular momentum. That energy and angular momentum gets extracted from the motion of the black holes. So the orbit is losing energy and angular momentum, so it shrinks. Eventually, the two black holes collide. And during the collision as well, more gravitational waves get emitted. So throughout this process, you're losing energy. If you're losing energy, you're losing mass. So the final black hole, energy and mass, E/mc squared. The final black hole you're forming from the collision, the total mass is less than the sum of the two masses you had before. So you are losing energy, and in the first collision we detected, it was about 3 times the mass of the sun that was lost and carried away by the gravitational waves. And it depends on the collision and the masses involved, how much energy we're losing in every collision.
Yeah, I mean, it's very hard to get a sense of the scale on the energy emission. But this is pure, mass energy being converted into gravitational waves. So one way to think about it is that, these events, for example, the one we just detected, this 1905-21, that was 8 times the mass of the sun in pure gravitational wave energy. Since we're the Bulletin of the Atomic Scientists, just to give you perspective, Hiroshima was, a fraction of a teaspoon of sugar in mass energy. That's how much energy was released. This is 8 times the sun. So you take 8 suns, all of that mass being converted to energy. It's astounding. Another way to think about it is if you take all the stars in the entire observable universe, not just our galaxy, but every galaxy in the entire observable universe, there is more energy being radiated by this black hole collision than all those stars. At that time, more power is, the black holes are much, brighter, if you like, briefly for, a fraction of a second. Yeah. But it's a phenomenal amount of energy, which we can barely hear by building the world's most sensitive instrument.
So mind-blowing. It's just amazing. So our next question is Gabriel Luis. We have Gabriel. All right, we're going to go to a follow-up question with Damir now. You're on mute.
Unmute. Sorry, my iPad keeps shifting out. Damien from Australia, 2 o'clock in the morning here, so a little bit sleepy. I'm a electronic sound designer by origin. I work in a library right now. I'm thinking of how we could use not just the LIGO's discoveries, but also some other cosmic observations devices. And Has anybody considered using microtones to downshift cosmic sources to a acoustic level? Because I mean, a few years ago there was a an acoustic rendering of the magnetic fields that were vibrating around the sun, downshifted to an acoustic level. And is there any way that anybody considered maybe even using the findings in quantum mechanics and quantum particle accelerators to downshift to a usable or acoustic level using microtones? Or is that too much of an ambitious question?
I haven't thought about this specifically, but in general, I would say that anything that has a frequency that evolves with time, any phenomenon that has a frequency evolution with time associated with it, one can always come up with some kind of a translation formula and bring it down to a sound. But particularly for the phenomenon you're bringing up, I don't know if anybody has done it and whether it builds any intuition in understanding the signals. For our case, it helps because as we only played two sounds, but the massive, when our gravitational wave mergers come from very massive objects, large masses, then the signal is short. It's more like a thumb. When the signals come from low mass objects like the neutron stars, then they last longer and they go to higher pitches, they're not lower frequencies. So the sound gives you intuition. So I don't know if for these other phenomena there is intuition to be gained. Daniel, I don't know if you know anything.
Yeah, I know. I mean, I would just echo what you're saying, which is, you know, it's the sound is an analogy, but it is the frequency content is key for our analyses. Like that's where all the information is, which is what we're using to figure out the masses and the spins and all the things that Vicky described. And so the way we actually do the analysis is often, if you like, in frequency space. We're really focusing on the spectrum, the full distribution of sounds, if you like, the harmonics, the chords, if you're thinking in a, audible way, that's where we do our analysis. And we look at the details of that structure. And that's how we get all the information we do.
So for our final question, we might have time for two more, but maybe a final question is Knox Long, who is in Chicago.
Hi. So my question is the following. So for these detections to have occurred, general relativity had to basically work, and all of the populations studies and everything are really exciting. But were there alternatives to general relativity that have been really limited, or have strong tests of general relativity that we were worried about actually occurred as a result of the observations, or is this really an astrophysical tool?
Yeah, I can start on that one. So as you're probably familiar, so we don't have any compelling alternatives to general relativity, but people are really trying hard because at the end of the day, there are some things that are a little mysterious about our account of the universe, including this dark matter and the dark energy. And so just to give you one example of something we've learned from gravitational waves, which I think is quite striking and very important, is that second movie I played, you might remember, it's the gravitational waves, and you hear the chirp, whoop, and then 2 seconds later, there's the ding from the gamma rays. And so the gamma rays and the gravitational waves arrive within about 2 seconds of each other after traveling through the universe for about 100 million years. Okay. So what that measurement told us right away is that gamma rays and gravitational waves basically travel at the same speed. Over 100 million years, at most, the slippage was only 2 seconds. And the fact that gravitational wave and the theory predicts, the conventional theory predicts that they should travel at exactly the same speed. And so what we think is it just took a couple of seconds after the neutron stars collided to make gamma rays. And that kind of, everything kind of fits. Okay. The fact that they travel at basically the same speed rules out a bunch of alternatives to general relativity. There have been a whole community of people writing papers trying to account for dark matter and dark energy by changing gravity a little bit. One of the most popular ways to do that ends up changing the speed of gravity, if you like, compared to the speed of light. We just ruled all those theories out immediately. I mean, it was carnage in theory space because of this very simple measurement where we knew right away, because we had gone the gamma ray burst, that these you know, they travel at the speed of light. So that's just, you know, one example. There have been other even more kind of what I think of as, you know, slightly convoluted. I mean, theorists can be very creative, and so people have predicted that there would be very strange effects when the black holes merge, and maybe they'll bounce off each other because they're not really black holes, or there'll be echoes, or there are all sorts of things that could happen in principle. So far, we haven't seen anything like that. We would love to. I mean, falsifying general relativity would, I mean, my background's in general relativity. I love the theory, but boy, if I could show that the theory is somehow wrong, that would be great. But that doesn't seem to be happening, at least so far. But, you know, as Vicky mentioned, we're going to turn back on. You know, we should mention there are the 2 LIGOs. There's also the Virgo detector in Italy. All 3 of those will be turning back on. And then there's also one in Japan that's almost ready to be turned back on. And then there's one in India that's being built. So all of these are going to turn back on. We're going to hear more things. And, you know, as soon as we turn back on, there could be surprises. And maybe we really will have to rewrite general relativity. It hasn't happened yet, but, you know, we'll see. Time will tell.
Well, I'm very excited to see what surprises you guys come up with next. And we're at the top of the hour. And so I want to thank Vicky, Daniel, and everybody that watched today. This was so fun to see everybody and engage in such a great conversation. So thanks to everybody. Thanks to the Bulletin. Kicking it back now to Hallie to wrap up. And again, thank you all for joining us.
Thanks so much. And big thank you to Vicky and Daniel for this conversation. And thank you to Cyndi for stewarding us through it. Don't forget to register for the upcoming program on October 21 and November 12. Both of them can be found on thebulletin.org. And last but not least, thank you to you all, the Bulletin's community, for participating with us this past hour. Ladies and gentlemen, we are adjourned.
Thank you. Bye.
Thanks, everyone, for all the great questions. This was really fun.